Microphones are transducers that convert acoustic energy into electrical energy. In this lesson, we discuss the different types of microphones and their operating principles, as well as how to select a microphone for a particular purpose. The operation of all microphones is based upon three building blocks: the membrane, the element, and the housing. The membrane of the microphone is the entity that couples with the air so that the changing pressure of sound waves is converted into mechanical motion. The element is the entity that converts the mechanical motion from the membrane into electrical energy. The housing not only holds the membrane and the element, but also provides the means for the microphone to be directional. The two most common types of membranes are the diaphragm and the ribbon. The diaphragm is typically a round, thin piece of mylar. The ribbon is typically a thin rectangular piece of foil that is corrugated to provide rigidity. There are two main types of elements as well, the dynamic and the condenser. The dynamic element is composed of a coil of wire suspended in a magnetic field. The condenser element consists of a capacitor which is tied to an internal amplifier circuit. The dynamic element works on the principle of Faraday's law in reverse. The diaphragm is connected to a coil of wire, and when pressure fronts hit the diaphragm, it moves, forcing the coil to move. When the coil of wire moves through the magnetic field, current is forced through the coil of wire. This current is otherwise known as an audio signal. Dynamic microphones can withstand very high sound pressure levels due to their rugged construction. The ribbon element is a thin corrugated piece of foil that is suspended between two magnets. When sound waves strike the ribbon, causing it to vibrate, a voltage is created in the same manner as with the dynamic microphone. In this way, the ribbon acts as both the membrane and the voice coil. It is a very light and delicate element, and as such it has very good sensitivity to small pressure changes and is easy to move. The ribbon element has a front and a rear, which makes it naturally bidirectional. The condenser element consists of two thin plates, one that moves and another which is stationary, which form a capacitor. When the sound pressure waves strike the movable plate, they cause it to move back and forth, which causes the voltage across the capacitor to vary. This voltage difference is the outgoing waveform. Condenser microphones require an electrical source to function, called phantom power. Phantom power is a 48-volt DC voltage supplied by a preamplifier. Preamplifiers on most mixing consoles commonly have phantom power. Dynamic microphones have a dynamic element, and as such they are best suited for vocals and drums in a live environment. They are more rugged and durable as they contain fewer delicate electronics than a condenser or ribbon microphone. Dynamic microphones are not as sensitive as condenser microphones and are best suited to close miking situations. A condenser microphone uses a capacitor as the pickup element. Condenser microphones are known for their high sensitivity and transparent sound. They are also rather delicate and cannot stand up to abuse like a dynamic microphone. Condenser microphones are most widely used in recording situations and are not best suited for live touring applications due to their high sensitivity and delicate nature. There are exceptions, but in general they are used primarily in recording studios. Condenser microphones can be classified into two main groups, large and small diaphragm. Large diaphragm condensers are used in studios for recording vocals and instruments, and in the live setting for instruments and guitar amplifiers. Small diaphragm condensers, on the other hand, are used primarily for instrumental pickup in both recording and live settings. Ribbon microphones are made by only a few manufacturers, but are making a comeback due to recent design innovations. Since their ribbon element is so light, they have high sensitivity and a very natural sound. Ribbon microphones are used primarily in recording studios due to their delicate design and construction. The directionality of a microphone is dictated by the housing, which holds the membrane and element. With condenser microphones, the directionality can be changed electronically. In order to make a microphone directional, perforations are made in the housing near the diaphragm. The perforations allow sound from the rear of the microphone to enter the housing and strike the diaphragm. While this is happening, that same sound from the rear also travels around to the front of the microphone, where it also strikes the diaphragm. The same wave striking the diaphragm from opposite directions, 180 degrees out of phase with each other, causes cancellation, and hence we have a microphone that only hears from the front. The more perforations there are in the housing, generally, the more directional the pattern becomes. For instance, a cardioid microphone generally has a single row of perforations, while a hypercardioid microphone has more, and a shotgun microphone has many more. Notice that an omnidirectional microphone has no perforations, which means that it has no cancellations, and therefore is not directional. A microphone's directionality is classified by its polar pattern, which is a diagram of how a microphone hears. A polar pattern is plotted on a 360-degree map, which shows directionality based on its sensitivity. The plot depicts the angles the microphone's sensitivity begins to roll off. There are three main pickup patterns: omnidirectional, cardioid, and bidirectional. Within each main type there are several variations. Typically, there is a symbol etched onto the microphone housing indicating its pickup pattern. Omnidirectional microphones pick up sound in a full 360-degree area from the front element of the microphone. These are truly omnidirectional in the low and mid frequencies, but become more directional as the frequency goes up due to smaller wavelengths. The cardioid pattern is the most common directional pattern available. It is known as cardioid due to the pattern's similarity in shape to a heart. A cardioid pattern excels in rejecting sound from the rear and partially from the sides of the microphone. This is beneficial when attempting to reduce feedback and bleed over from other sound sources. A hypercardioid pattern is more directional than a cardioid and supercardioid by further reducing the side pickup. The drawback of the hypercardioid pattern is that it has an inherent lobe to the rear, which is not highly sensitive, but must be considered when using this type of microphone. The bidirectional or figure 8 pattern resembles two cardioid patterns placed back to back. It is moderately effective at rejecting side noise while equally picking up the front and the back. This pattern can only be found with microphones that have two diaphragms back to back, typically large diaphragm microphones. This pattern is well suited when recording a duet. A shotgun pattern is a highly directional pattern used for sporting events, dialogue in TV and film production, and sound effects. Some condenser microphones feature a switch that allows the user to select one of multiple pickup patterns. This is achieved by manipulating the properties of the diaphragm electronically. This versatility allows the microphone to be used in various applications. One characteristic of directional microphones is known as the proximity effect. The proximity effect is an exaggeration of the low frequencies that occurs when the sound source is too close to the microphone. This makes the sound source boomy and prominent. Microphones are available in many shapes and sizes that utilize different technologies in order to cater to a specific audience or purpose. The most common type microphones are handheld, lavalier, instrument, and head-worn. Lavalier microphones are mostly used to pick up speech, particularly in the broadcast and religious markets. However, when the speaker is someone who frequently moves around and rotates their head, the lavalier microphone is often insufficient to capture all of the speech. A growing trend is the use of head-worn microphones, which move with the speaker's head and are therefore more effective than lavaliers. Head-worn microphones are typically worn over the ear and extend down the cheek of the user. Head-worn microphones are widely used in the theater and drama applications. Some specialty microphones that are used in specific situations are the shotgun mic, the boundary mic, and stereo microphones. A shotgun microphone is a specialty microphone used to pick up a source from a distance without accepting surrounding sounds. This is achieved by using a very narrow polar pattern. A boundary mic is a microphone attached to a thin metal plate. When placed on a surface, it picks up both direct and reflected sound in phase at all frequencies. The size of the surface has an effect on the low-frequency response of the microphone. Stereo microphones are microphones that contain two diaphragms which convert the incoming acoustic signal into two audio signals. The diaphragms are often rotatable with selectable patterns to achieve specific arrangements used in two-channel recording. Microphones' properties include pickup pattern, sensitivity, and impedance. A microphone sensitivity is the amount of output energy measured in volts the mic will produce using a standard input signal level. This voltage determines how much the microphone signal must be amplified to reach line level. Impedance is the resistance in an electrical device which is measured in ohms. Symbolized by the letter Z, impedance can be measured at either the source or the load. Microphones are low-impedance devices, or low Z, except for a few existing vintage microphones that have high impedance. Frequency response is the range of frequencies a microphone will reproduce. Most microphone literature includes a graph of the microphone's frequency response. Whether the frequency response is shown as a graph or as text, it should list a variance, such as 20 Hz to 20,000 Hz plus or minus 3 dB. Some microphones incorporate a roll-off switch, which cuts or steadily decreases the microphone's response. This feature is effective to limit or decrease the amount of extreme low-frequency pickup. Microphones are used in a number of different applications. Depending on the application, the engineer might choose to use a dynamic or a condenser, a microphone with a specific type of frequency response or sensitivity, and a particular pickup pattern. As with anything, selecting the right tool for the job is important. The same holds true for microphones. Aside from experimentation, the rule of thumb is that condenser and ribbon microphones are used primarily for recording purposes and high-quality reinforcement applications such as overhead drum mics, choir pickup, orchestral instruments, and guitar amplifiers. Dynamic microphones are best suited for high SPL applications which do not require high sensitivity. They perform best capturing live vocals, drum sets, and rock and roll type instruments. There are some basic guidelines when positioning a microphone, but the most important thing to remember is to experiment with different microphones and positions until you achieve the desired sound. Feedback plagues all audio systems at some point. It is the job of the engineer to prevent feedback at all costs. Using directional microphones and placing them properly is the first step to preventing feedback. Keeping the number of open microphones to a minimum reduces the chances of feedback as well. The laws of physics state every time you double the number of open microphones, you decrease gain before feedback by 3 dB. It is critical to mute microphones that are not being used. It should be noted that more is not always better. When positioning microphones, it is important to look at the big picture, not just to focus on where you perceive to be the best pickup location. The best method to find the preferred microphone location is to have the musician play while someone moves the microphone around the instrument. You'll often find that preconceived notions may not be the best. For instance, instead of miking the bell of a saxophone, try miking the body where the keys are. This reveals a natural tone and often gives a better impression of the sound of a saxophone. Picking up large groups of singers or a big band can oftentimes be achieved by using a pair of high-quality microphones in a stereo configuration. This is often the best method to create a stereo image and soundstage in a recording. Also, more headroom will be available by using fewer microphones. Several spaced microphones work well in a reinforcement situation. Each mic can be mixed to an appropriate level to represent the group as a whole. Stereo recording techniques are used when a matched pair of microphones is available to capture a sound source. These techniques include the XY, ORTF, mid-side, bloom line, and the spaced pair. There are specific guidelines for each of these techniques to achieve the desired results. Each has a different result, and experimentation is encouraged to discover preference. Audience response microphones are used in recording and broadcast applications as well as for in-ear monitors. Their purpose is to give an impression of the audience reaction and participation. They are typically hung from the ceiling above the audience, but can be stand-mounted and placed on stage facing the audience. Audience response microphones are also used to help capture the acoustics of the space where the performance is taking place. Where do you start when miking instruments? Knowing the only rule is to listen, here are a few guidelines. The grand piano is a difficult instrument to capture due to its size and large dynamic range. It can also be played in a large variety of styles, ranging from classical to rock to jazz. Each of these variables plays into how the instrument should be mic'd. It is best to have a variety of microphones available, as each can lend its sound to the overall outcome. Techniques for miking a grand piano range from simple to complex, with as few as 2 and as many as 20 microphones being used on a single piano. If we look at the top view of the piano, we can see the length of the strings and the natural progression of frequency across the instrument. The low bass tones are produced on the left side of the instrument, where the longest strings reside, and highs opposite them on the right side. As such, we want to use appropriate microphones for particular frequency areas. A large diaphragm condenser microphone will capture the full tone and timbre of the bass notes. A small diaphragm condenser microphone will best reveal the higher frequencies and attack. The fatness and fullness of the mid-frequencies could be captured by using a dynamic microphone, and the attack and overtones with a condenser microphone. Wireless microphone systems have become highly sophisticated systems capable of delivering the same performance and reliability of wired microphones and providing increased mobility. The basic fundamental purpose of the transmitter and receiver is to provide freedom from a microphone cable. The trade-off is the fairly narrow band of radio frequencies available for transmitting the audio signal to the receiver without interference, and the need of a battery to power the transmitter. Wireless microphone systems operate in either the very high frequency band, VHF, or the ultra-high frequency band, UHF, as prescribed by the Federal Communications Commission, or FCC. Consequently, wireless networks and UHF television stations share these bands. The critical element for proper wireless operation is identifying a clear frequency in the venue's location. The majority of wireless system issues stem from frequency-related intermodulation and interference, not the microphone itself. A frequency scan should be performed prior to investing in a wireless system. A frequency scan will identify active Wi-Fi, television stations, and possible intermodulation problems. Care should be taken in choosing a usable frequency for each wireless system. Most mid-priced wireless systems are frequency agile. They allow the user to select which frequency they wish to use. Many high-end wireless systems include a frequency scanner that will identify problematic frequencies in the immediate area and allow the user to select from a list of clear channels. This type of system is most useful in touring applications. As with any battery-powered device, it is important to implement proper battery rotation in order to prevent unwanted issues during a performance. It is best to install newly tested batteries prior to each performance. Most wireless transmitters incorporate a low battery indicator, which provides a quick visual warning if the power source is inadequate. Microphones are the primary transducer that converts acoustic energy into electrical energy, which begins the audio signal path. Selecting a quality microphone well suited for the application is very important to maximizing signal quality. Microphone placement is important but is largely based on preference and experience. Experiment with placement to find a sound that is pleasing. Keep the number of open microphones to a minimum in order to decrease the chance of feedback and sound degradation. Perform a thorough frequency scan prior to selecting a wireless system channel. Always install fully charged batteries prior to performance time. When it comes to microphones, remember, there are no rules, only guidelines.